All right, so welcome back. Today in this video, we're going to be looking at some more mechanics of materials, but we're going to be focusing specifically on stresses and strains. So I went in depth on shear moment diagrams in my last video. So if you have not seen that, make sure you check those practice problems out. But today we're going to be looking at stresses and strains. And so let's go ahead and dive right in. So, number one says calculate the shear stress in kilonewton per meter squared in a material subject to a shear force of 800 newtons over an area of 0.03 meters squared. So, what information are we given? We are given our shear force. We are also given our area. Okay. Over this material. So we got a force that's happening on a specific area. So it would kind of be like this, right? Imagine that this is our area, this little random circular pellet on the ground, and we got a force coming down on it. Maybe for it to be easier to see, it's just a different. So we got this force coming down on that circular pellet material, whatever, and it's coming down at 800 newtons. And they would just want us to find the stress acting on that, and that's typically a force over an area. They want our answer to be in kilonewtons per meter squared. So I'm going to look up shear force, shear stress, maybe. We're trying to find shear stress, so let's look up shear stress. All right, shear stress is denoted as that weird T. It says that here, but that formula, don't know if that's really going to help me out. Don't know what this is searching for right now. Okay, shear stress. Shear stress is denoted again as T over G. We don't have shear modulus, right? G in this case is shear modulus, and then shear strain. We're not given any of that information, so we wouldn't use that formula. Okay, shear stress. All right, shear stress. Polar moment of inertia. We're not given that information. This is also not a circular solid or shaft. All right, shear stress equals T over A. What is T? Shearing force. We're given shearing force, and we're given A, which be the area. Okay. So let's look at this. So the formula that we need, trying to find, the information that we're trying to find is the shear stress. The formula that we need is going to be shear stress, just T, is equal to is the weird T over the, is equal to big T, which we'll just write them out separately over A because that's confusing. So T in this case is equal to our shearing force, which it says here's shear force. which is equal to 800 newtons. Our A is equal to 0.03 meters squared. All right, so how do we get our shear stress? Well, we just plug and chug. Now we have all the variables that we need to get our unknown, or the value that we're trying to find. 0.03 meters squared. And this is going to give me 26,666.66 Newton per meter squared. Okay. What's wrong with this? If we get this for our answer, why does it not match, right? Well, they want us to calculate our answer in kilonewtons per meter squared. We have newtons per meter squared. So how do we get that in the right units? Well, we just need to do something simple as of how many kilonewtons in a newton. 1,000 newtons are in 1 kilonewton. That's what that means, right? Then that equals 26.66 kilonewtons per meter squared, which is the units that we need it in, right? And so I'm getting A. All right, let's look at number 2. All right, so it says for the following stress strain curve, where does necking occur? All right. So we have this diagram, this famous diagram. We got A to the point, we got B calling out something along this stress and strain curve. But we're trying to find where necking occurs. All right. So this is one that you're just going to have to know. You will need to know what A, B, C, D, and E are. So I'm just going to go through them here, and you just need to make sure that you memorize them. All right, so A is yield strength. All right, so at point A, that is its yield strength. So as strain, increases, and as stress increases, typically this is what happens on like a piece of steel, right? It's the stress strain curve for probably some steel. As you increase your stress, as you increase your strain on that steel, pretty much you have a maximum strength before the steel is going to change, right? And so if you've ever, let's say you've had a paper clip, right? You can pull on that, you can push or pull on that paper clip until a certain point. But if you really pull it and pull it out of its, spiral loop per se, then there's no way to get it back in that original shape. And so that's the point at which you're hitting your yield strength. All right. So what is B? B is your ultimate strength. Okay. Ultimate strength meaning that, okay, you can keep adding, strain to this thing, right? You're adding strain. It's not going to return to its original shape, but at a certain point, it's beginning to, the stress is the maximum stress that it's going to be, right? If it's happening here, that's the max stress that it can possibly hold before other things begin to happen. Okay. Point C is where the piece fractures. And a fracture just means to break, right? So at a certain point, keep putting strain on it. It's gonna break, right? That paper clip is gonna break. Whenever you're putting a massive amount of stress or strain, it has this point where it's definitely gonna break. Part D is necking, which is what the question asks. Now, what does necking look like? So if I have a bar, right? And I pull on that bar. Well, first, the bar may not, well, I don't know how it just turned my line straight, but that is cool. First, the bar, over a period of time may not change, but eventually it could stretch, right? And begin doing something like this. And basically, okay, I don't like the tool anymore because do something like this. All right. And it's basically you're pulling this piece so much that it's beginning to neck, right? Necking is that small kind of squeezing motion that takes place where you can see the middle of it get narrower and narrower, narrower until it just decides to break, right? And that's where the fracture happens. All right. And then E would be strain hardening. And that's where it's just building up just a little bit more until it reaches its ultimate strength. So strain hardening. All right. So these are key things that you're going to need to know for this. Answer is D. We're given our curve, right? We're trying to find necking. And you had to have some prior knowledge for a question like this. Something that you're going to need to know on the exam. They're going to ask you. So just know what happens at each phase and you should be good, right? E is a phase. D is a phase. Like necking is a phase, right? Happens from just there to there. And it's separated by these little bars, right? Strain hardening is a phase. So it's pretty much happens from the time that it hits its yield strength to its ultimate strength. Okay. All right, let's look at number 3. All right. This one says calculate the maximum stress in a solid circular shaft with a diameter of 20 millimeters when a torque of 100 Newton meters is applied. Okay. All right, so first of all, what am I given? Well, I am given a few things. So I know it's a solid circular shaft. That may be important given the diameter. And I'm also given the torque. Okay. I'm trying to find the max shear stress. Okay. So how do I get the max shear stress? Well, I know that torque, I may need torque. So I'm going to search torque. Maybe not. So I go through and see if anything can. This is for brake power. So okay. Shaft. We got T. Okay, we got. This is a circular solid shaft. So this is a hollow, thin walled shaft. So maybe a circular. Okay. Okay. Torsion stress. Max stress. Okay. In a circular solid shaft is T is equal to, or weird T, stress is equal to T times R over J. So are we given a radius? Are we given T? What is T? T I know is torsion, or torque, rather, not torsion. T is equal to torque. All right, so we have, so we're given torque. Do we have R? What is R? R is the radius. Well, we're given diameter, so we are given torque. Are we given? I mean, we are given the radius. Are we given J? J is the polar moment of inertia. So don't know if we're given that, but can we use a diagram to get J? So I believe I'm in the right spot. So T, or stress, equal to T R over J. Okay. Let's see if there's a diagram for shafts. Or it's just a circular, it's a solid circular shaft. So we just need a, really the, can I get the polar moment of inertia for a circle? All right. So where would that be if I could? I'm assuming it would be in mechanics of materials. maybe not. So try statics. Yes, statics. Okay. So we may be revisiting statics to get the polar moment of inertia. And that's represented by J, right? So now I have a circular solid shaft. I also know that is represented by J. So J is equal to so let's just write out our variables that we have. So T, big T is equal to 100 Newton meters. R is equal to, I'm going to put everything in meters. So R is equal to 10 millimeters or 0.01 meters, right? Now I want to use everything, get everything in the same unit. So 100 Newton meters, 0.01 meters. That way things can kind of cancel. So I typically do that. And then J, right? J is equal to, okay, pi a to the fourth all divided by 2. What is A? A is the radius. So J is equal to pi times, so A is equal to 0.01 meters. So pi times 0.01 meters to the fourth all over 2. All right, so what do you get? What do I get for J? J is equal to 1.6 times 10 to the negative 8. So I get a really small number, meters to the fourth. Remember this, your units are going to stay where they're at. So if I put 0.01 meters and then that's all to the fourth power, those units go with it. So get a really small number, 1.6 times 10 to the negative 8 meters to the fourth. Okay. And then now I have all the variables that I need to be able to solve for my stress. All right. So stress is equal to T, 100 Newton meters. What is R? Times 0.01 meter divided by 1.6 times 10 to the negative 8 meters to the fourth. All right, and if you multiply, or if you divide a somewhat decent sized number to a really small number, it's going to make the number really big. So when I do this, a really big number. So I know that it's 6.25 times 10 to the 7th power. What are my units? All right. So if I know that I have a meter and a meter, so that's going to be meters squared over meters to the fourth. So those cancel and leave me with something over meters squared. Okay. And then what's that something? Well, we still have newtons available. So newtons doesn't cancel with anything. But those are the units I need. It's always a force. Stress is always force over area. All right. So I end up getting B for this one. All right, so a little tough. Just have to get your bearings right, knowing where to pull formulas from. Don't get scared. Units are a big thing with this. So everything typically you want in meters or newtons. If it's feet, typically it's feet and pounds. I'm gonna keep things pretty much the same. You don't want it to be in kilonewtons unless they're asking for it to be in kilonewtons or whatever the case is. So, this concludes this section of the mechanics of materials review. In the next video, we'll be looking at some deformation practice problems. See you in the next one.